Good day, everyone. My name is Otto Mohamed Sani, Physics Department Lecturer. I'll still be taking you on Physics 121. General Physics 2, we'll be talking about sound waves. From the term sound wave, we already know that sound wave is a mechanical wave. Sound wave is also what we call a longitudinal waves. So, what is sound wave? We're going to talk about, in this section, we're going to talk about more about sound wave and its difference in transmission. That is, the differences that occurs when you're transmitting sound wave in these mediums. We have the solid medium, we have the liquid medium, and we have the gaseous medium. We're also going to talk about intensity of sound, the pitch of sound, the quality of sound, the loudness of sound. We're also going to talk about propagation of sound in these mediums. That is, we're going to do maybe 1 or 2 calculations on the propagation of sound using their formulas. We're still going to discuss about beats, music, and noise. We're going to also differentiate between ultrasound and infrared sound. So with this, I would like to begin my lecture with sound wave. It's a sound wave is a mechanical wave. Why? Because if, for instance, I tend to beat a drum, the moment I beat a drum, what I've done is that I've used a medium. For me to beat a drum, I need a drumming stick. The moment I beat that drum, it's going to make sound, and it's going to create a wave, sound wave. So beating that drum, I've used a medium, and that medium is a solid medium to create that wave. So I can say that sound wave is mechanical in nature. Sound wave is also longitudinal. Why? Because the direction in which sound wave travels is the same as the direction in which it was displaced. That is, the direction of displacement is equal to the direction in which the wave will travel. Also, I can say that the direction of displacement is at an angle 0 degrees in which the direction in which the wave was displaced. So therefore, we can say sound wave travels from one medium to another. But please take note, sound wave does not travel in a vacuum. A vacuum is what we call a free space that is free of any of these 3 mediums. So since there is no medium to transmit or propagate wave, sound cannot exist or travel in a medium, in a vacuum. So we're going to now talk about how sound wave travels in each of these mediums. Sound wave travels more in a denser medium, that is in solid medium, than in a liquid medium, and also than in a gaseous medium. That is why if you see the speed of sound wave, it is approximately V is equals to 6,000 meters per second for solid. For liquid, V is approximately 1,480 meters per second for liquid. And for gas, V, the speed of sound, is 330 or 343 meters per second for gas. Now, if you look at it, you will discover that the speed of sound is higher in a solid medium, which is a denser medium, than in a dense medium, and than in what we call a less dense medium. With this, you can be able to tell that sound travels more in a solid medium than in a liquid medium. Please, if you look at these 2 values, you discover that the values are different. Why? We have 330 meters per second and we have 343 meters per second. The 330 is for wet air. The 343 is for dry air. That is, when there is increase in temperature also affects the speed of sound. If you look at it, when it's wet, the sound is lesser than when it is having a temperature. For dry wave, for dry air, the speed of sound is higher. With this, we can now therefore say that sound travels through all these 3 mediums, and without the mediums, sound can never travel. So if there's anything that does not have any of the mediums, sound will never travel there. So we'll go to the next part, which is the intensity of sound. The intensity of sound. For you to talk about intensity of sound, you need to make mention about what we call the sound power. Why? Because the sound is the ratio of power of the sound per the area in which the flow of sound is going to. Therefore, I can say that intensity is the power of sound per unit area, and it is measured in watts per meter square. Watts per meter square. If you look at this derivation also, power is known as what? Energy all over what? Time. So if I substitute this, I can also say that intensity is the energy all over area multiplied by time. So this is the same thing as this. If this is equation 1, this is equation 2. With this, you can see that sound, which is also a wave, is having a relationship with energy. That is, if you want to get high intensity of a wave, you need to have a sound that has high power. And that is why if you look at the back of every musical instrument, you see there is a specification there whereby they tend to tell you the power of sound is so and so. In most cases, you might not see it in watts per meter square, but rather you see it in decibel, dB. The reason why you see it in decibel is because the sound has been converted from watts per meter square to decibel through using what we call 10 log base 10 of intensity divided by the standard hearing capacity or ratio, which is I naught. When you do the calculation, that is, let's say for instance, I have 50 watts per meter square. All I need to do is substitute 50 here, and this has what we call 1 times 10 raised to power minus 12. If you put it there and do the calculation, you will get your value or your answer in decibel. So you see most musical instruments have their specifications in decibel. So we'll go to the next one. Power is the intensity of sound has a relationship with so many factors. Number one factor is that intensity of sound has a relationship with amplitude. The higher the amplitude, the higher the intensity of sound. From the equation I'm going to state here. The equation is I is equals to half density omega squared V A squared. Okay. Now, if you look at this, these factors also, this is another equation to calculate for intensity of sound. So we call it equation 3. There will be no time for us to start deriving these equations, but you can still find out these equations from your textbooks. Now, if you look at this equation, you can see that I is directly proportional to amplitude, the square of the amplitude. So I can say that this is a condition that influences intensity. That is, the higher the amplitude, the higher the intensity. So therefore, I can say that the intensity is directly proportional to the square of the amplitude. That is, if a sound wave has an amplitude, let's say 2, the intensity which is related will be twice of that amplitude, which will now be 4. That is, it has increased. When the amplitude increases, intensity also increases. The second condition is that, we have also talked about it before then, is density. We said sound travels more in a denser medium than in a less dense medium. And we said solid has high speed in terms of sound. Therefore, if solid has an high speed because it is denser, it means that also the intensity will have high intensity. Why? Because when density increases, intensity also increases. That is, if a material or a medium has high intensity to high density, it will also have high intensity. If a material has low density, that is less dense, its intensity will also be low. We'll go to the third one. Intensity is directly proportional to the speed of the sound. If the speed of the sound is high, let's say the speed of sound in solid medium is 6,000 meters per second. Therefore, the intensity too will be very high compared to when the speed of sound in a liquid material is 1,480. You see, the speed of sound is not up to that of when it was in the solid material. So therefore, I can say that the intensity is directly proportional to the speed of sound. That is, higher speed, higher intensity, lower speed, lower intensity. And for you to get an higher speed, you need higher density. So we'll go to the fourth one. The intensity is also directly proportional to the square of the angular frequency. Why? Because if the angular frequency, which is 2 pi f, so we're going to get 2 pi f squared, which is 4 pi squared f squared. For you to get high angular frequency, it means frequency must be high. And when frequency is high, intensity is also high. So with this, I can say these are the factors that contribute or facilitate the influence of intensity of sound. So we'll go to the next one, which is the pitch of sound. The pitch of sound, or the pitch of musical sounds, depends on frequency. And that is why you discover that if you are in the church choir, or if you're where they sing music, you see that everybody has his own different pitch when they're singing their songs. Some people's pitch tends to be very high, while some people's pitch tends to be very low. It means that the sound they create from their mouth is of low frequency to have created low pitch. And for those with high pitch, it means that the sound, their frequency, in which the frequency of the sound they create is very high. Now, please take note, a very high frequency will give you a very high pitch of sound. A very low frequency will give you a very low pitch of sound. Quality of sound. Quality of sound is easily distinguished through the ears, whereby the ear tends to get the same pitch and the same loudness. And also we can say quality of sound depends on the overtone present in a note. It is just like somebody singing a song, another person is murmuring something else, or somebody is saying something that is not relating. Your sound is able to distinguish if this sounds coming from different places or from different persons is having the same pitch or not. The moment that sound coming from different sources is not having the same pitch, your ears tends to feel it is noise. It can now differentiate, is it a music or a noise? And what is the difference between music and noise? Music is when the ears is able to differentiate, is able to get a regular vibration of these waves. And noise is when it does not get irregular, it is irregular. So you hear it like a disturbance. Now we'll go to the next one, which is called loudness. For loudness is talking more about the magnitude of sensation in which the sound gets to the ear. And loudness also depends on intensity. Now, how do you know that loudness depends on intensity? If a siren is coming close to you, you tend to discover that the loudness increases. And when the siren now passes you, you discover the loudness or the volume, we call it volume, tends to reduce. That is, whatever sound that siren is making is becoming too low. So therefore, we can also say that loudness depends on the square of amplitude. That is, for soft sound, it has smaller amplitude. For large sound or loud sound, it has larger amplitude. So we'll go to the next one. The next slide, we're going to talk about the next slide we're talking about is the equation that we're going to solve. For this equation, the question says that a point source emits sound wave isotropically. The intensity of the wave is 0.5. The intensity of the wave is 2.5 meters from the source, which this is what we call the distance, right, from the source. Whereas they said the intensity is 1.91 times 10 raised to power minus 4 watts per meter square. Assuming the energy of the waves are conserved, find the power. So we are asked to find the power. From the statement, there is need, after getting this information, which is called data, there is need for us to now know that intensity is equals to P all over A. Now we are asked to find power. We are given intensity, but we don't know the area. Now, for a sound to have been created or to have been emitted isotropically, it means that the source of that sound is spherical. And when it is spherical, the area of the sound is going to be 4 pi r. The area of the sound is going to be 4 pi r squared, please. So if the area is 4 pi r squared, the radius is given as 2.5 meters. Please be careful with the conversion. So I'm going to substitute the radius there, which is 4 pi, open bracket, 2.5 squared. This, with my calculator, it will give me, I'll get with my calculator. Okay, let's just substitute let's do cross multiplication. If I do cross multiplication, P is equals to I times A. And what is A? A is P is 1.91 times 10 raised to power minus 4 times 4 pi multiplied by 2.5 squared. To get P, if you do the calculation for P, you will get 0.1. You get 0.015. 0.0115 watts, you get 0.015 watts. Okay, so with this, we can now say that the power of the sound is 0.015 watts. The examiner can also choose to ask you to calculate for what we call to deduce the value for the intensity in decibel. If you are asked to deduce, it is not on the slide. If in case you're asked to deduce the intensity of the slide to decibel scale, all you need to do is say beta dB, open bracket, is equals to 10 log, open bracket, base 10 of I all over I naught. What is this? 10 log base 10, open bracket. What is I? I is 1.91 times 10 raised to power minus 4, close bracket, all over 1 times 10 raised to power minus 12. If you do that, your answer will be in decibel scale. So it means you have also deduced the value for this sound in decibel scale using the intensity. So with this, we'll go to the next slide. The next slide is now talking about the propagation of sound. And on the propagation of sound, it says when sound passes through a solid medium, what happens? Now, this is just talking about the speed of sound as related to density and also what we call the Young modulus or the Bach modulus. Now, for the first medium, the speed of sound when it passes through a solid medium is the square root of Young modulus all over density. That is, if you're given a question whereby you are asked, calculate or find the speed of sound when the Young modulus is so, and the density is so, and so. If in case the examiner chooses not to give you the values, let's say for instance, instead of giving you Young modulus, the examiner now says it is tensor stress all over strain. That is, he gave you stress and strain, and he says, you need to find what is Young modulus, right? The same thing, density might not be given to you. So you know that density is mass all over volume. So therefore, we can substitute these values inside here, and the equation will still work for us. So we'll go to the next one. Light as propagated, or sound when it is propagated in a liquid medium. When sound is propagated in a liquid, this is a solid medium, this is a liquid medium, equation 2. Now, when light is propagated in a liquid medium, it is the square root of bulk modulus all over density. So you might also be asked to find bulk modulus using this equation. That is, the examiner will give you the speed of sound in the liquid medium. It will give you the density of that liquid, and it will now ask you to find bulk modulus. How do you find bulk modulus? You cross multiply. First of all, before you cross multiply, you take the square of both sides. So it becomes V squared is equals to B all over rho. If you cross multiply, B is equals to V squared rho. So you see, this equation can also help you to solve for bulk modulus. So we'll go to the last one, which is the third equation. The speed of sound in a gaseous medium is V is equals to square root 3RT all over M. What is R? R is what we call the molecular gas constant. T is what we call temperature. M is what we call the mass of the gas. With this equation, we can also solve for the speed of sound. We can also solve for the speed of sound using this equation, or the square root of gamma P divided by rho, whereby gamma P is what we call the ratio of the specific heat capacity at constant pressure to the ratio of specific heat capacity at constant volume. That is, gamma is equal to Cp all over Cv. P is called pressure. Rho is called the density of the gas. So with these equations, we'll try as much as possible to solve either one example from this question by God's grace. But in case we don't solve, you might see a particular solved question in your PDF document. So we'll go to the next slide. The next slide, okay, there's an example for this. If you look at the example, which is on that slide, you'll see that the example is talking about what is the bulk modulus of a distilled water, that is 3.20 grams of distilled water which occupies 22.4 liters. And the speed of the sound in the distilled water is 1,480 meters per second. First of all, there is need for you to do conversion. That is, you have to convert 32.0 grams to kilogram. And how do you convert? For you to convert, you have to divide by 1,000. You have to divide that equation by 1,000. The same thing, there is also need for you, that is, let's try it. If the mass, M, is 32 grams, divided by 1,000, I'll get 0.032 kilogram. I believe that is clear. So the next thing they talked about was liter, which is, liter is volume. For the volume of that water, V, the volume is given as what? 22.4 liters. We also need to convert 22.4 liters into millimeter cube. because it is volume. Volume is length times breadth times height. So it's millimeter cube, is meter cube. So to convert this to meter cube, you divide by 1000 also. If you divide by 1000, you get 0.0224 meter cube. With this, we can now find density. Therefore, density, which is mass all over volume, is equals to 0.032 divided by 0.0224. This will give you 1428.5 kg per meter cube. With this, we can substitute it inside the main equation that says that for the speed of sound propagated in liquid medium, which is V, is equals to the square root of bulk modulus all over density. We are asked to find bulk modulus, and we're given the speed of sound. So we can now say that we have derived it, whereby we say take the square of both sides, V squared is equals to bulk modulus all over rho. Therefore, bulk modulus is equals to V squared multiplied by rho. Now, what is bulk modulus? Bulk modulus is 1480 as given from the question, squared, multiplied by density, which is 1428.5. If you do this arithmetic correctly, you will get 3.13 times 10 raised to power 9. And this is, the unit is in newtons per meter square. Newtons per meter square. So with this, we have come to the end of that particular calculation. That is, we have been able to calculate this. So you also get questions. Please and please, sometimes the examiner might choose not to give you the value of density, just like the way they did not give us. But they gave us parameters to use it, like mass and volume. You can see we have to do conversion. That is, converting grams to kilograms, converting liters to meter cube. So please and please, there is need for you to know how to know your measurements and how to do conversion. So we'll go to the next slide. The next slide now is talking about, beats. For beats, we said beat is a periodic variation in the loudness of the sound, and it depends mostly on frequencies. Whereby you hear two notes having the same frequencies, it's called beats. That is, for instance, now, let's say somebody is beating a drum, the other person is playing from a guitar, and these two sounds are having the same frequencies. Before you know, a beat is created. Now, beat depends on frequency, whereby we can now say that the beat frequency, which is F beats, is F1 minus F2. That is the note from F1, note 1, that is, to get the frequency of beats, which is the beat frequency, is F1 minus F2. Please take note, the frequency of F1 is always higher than F2. Therefore, you will see a small example there, whereby it says example 1, two tuning fork of about 206 Hz and 194 Hz are played or are sounded simultaneously. Calculate the beat frequency or the frequency of the resultant beat. Now, if this one is 206, this one is 19194, the beat frequency will give you what? The beat frequency will give you 12 Hz. So that's how to find frequencies of beats. So we'll go to the next one, noise and sound. Go to the next slide, the noise and sound, or the music and noise. For music or for noise, first of all, noise is whereby there is an irregular vibration, or there is what we call a no fixed frequency of vibration, whereby whatever that person is making is causing a nuisance in your ears. Why? Because the frequency is not fixed, or is not constant. So therefore, we can now say that the ear is able to distinguish between music and noise. Why? Because noise is whereby somebody is playing a music, it is in form of a music, let's say, or a sound that is not having regular frequency. Let's say somebody is singing, hey, and you're not getting the frequency as being constant. We can call it noise. But for music which is originated from objects, has what we call a uniform vibration, or its frequency is constant, or it has a regular vibration in form of a way whereby the object is creating that sound as a frequency that is constant. Therefore, we can now say that the difference between noise and frequency is that noise is not having a regular vibration, whereas music is having a regular vibration. Also, we can say that the frequency of the noise is not constant, whereas the frequency of music or musical sound is constant. So we'll go to the next slide and we'll talk about echo. Echo simply means the reflection of sound, whereby you talk in, let's say, a room that has arched surfaces. The moment you talk in a room that has arched surfaces, you tend to hear yourself again. Let's say come. You hear yourself saying come. It means your sound has hit a strong surface and it has reflected back to you. In some ways, a layman will ask you, oh, please, what is echo? All you need to tell him is that you hearing yourself again after saying the said word within a time interval. And that is why you see most studios, if you go to a studio, let's say a typical example of a studio we have is the one in Falafia here at the e-learning center. You see that inside the studio is covered with foam. Why? Because they are trying their best to cover the hard surfaces to reduce echo. Because if you don't reduce echo, you will spoil the recordings you're making during your online lectures. That is, when we're doing online lectures, you keep on hearing the lecturer repeating the same word twice. Maybe he has said come and he's continuing with his lecture, you still hear the come he has said again repeat itself. That is echo. So in order to reduce echo, it is advisable to build a studio that has soft surfaces. Also, the ceiling can also be perforated. If you go to some studios, you see that their ceilings are perforated. It is because they are trying their best to reduce echo. Echo might be a disturbance to some of you, but it has its own uses in physics. Number one use of echo is that we can use echo to discover the depth of an ocean or sea. For some of us that don't, we just go into rivers and swim. We don't even know the depth. For you to discover the depth of a sea or ocean or river, you can use echo. What you do is that you send the sound downward using a device. It now reflects back that sound back to you. You're measuring the time and you're able to now tell how long it took that sound to be reflected back to you. So we can use echo to discover the depth of ocean or sea. And the device is what we call the echo sounding. Another way you can use echo, which is of importance in physics, is that you can use echo to discover the cracks in metals. Please, for all metals you see that are used during construction, some of them have cracks that might not be visible to your eyes. But with the use of echo, it will tell you whereby a metal that has been constructed has cracks. We can also use echo in the exploration of oil and petroleum. Also, we can use echo in military operations. That is why if you look at the submarines, you see that the submarines make use of echo with what they call the radar. The radar which tell you the locations of the enemy. Why? Because for the ships of the enemies to move or to flow on the river, it makes a sound. The sound coming from the engine is being sent to the other ship or the submarine. So with that, echo is of use during military operations. We'll go to the next slide and we'll talk about the disadvantages of echo. Because echo is the reflection of sound wave, echo is not desirable during even our online recordings. That is why if you go to the studio or auditorium, you see that they are made up of soft surfaces. There are a lot of windows. There are a lot of tissues, that is soft tissues, so that it reduces echo. Because whenever you're lecturing in an auditorium that has echo, you discover that even the students are not comfortable. The lecturers are not comfortable. Echo also is a disturbance when communicating, especially through your phones. If you're making a call and the phone and the sound you're sending to the signal you're sending to the receiver is echoing, you see that at that moment, even your ears is irritating you. So immediately you cut the call and try again. Why? Because it is echoing. And methods in which you can use to prevent echo or reduce echo. We said number one method you use in preventing or reducing echo is padding the wall. What it means is that for you to pad the wall, you put soft tissues. This is a studio. If you look at its studio, it has soft tissues. These tissues on top of this wall, on the wall, are soft to prevent reflection of sound wave when it hits the wall. Now, in the studio, you discover that there is no echo because the walls have been padded with soft foams. Second way of reducing echo is to make sure that there are windows, more windows and louvers in either the studios or auditoriums. For you to reduce echoing in auditoriums, you can increase the numbers of windows. Also, the ceilings in those auditoriums should be perforated. That is, instead of having your normal ceilings, the ceiling should have holes, a lot of holes. That way will reduce the hardness of the ceiling, whereby it will also reduce echo. We'll go to the next one, revibration. Revibration also occurs. This is a bit different from echo, but it's almost similar, but a bit different. Why? Because revibration is as a result of sound wave being preserved after the source of the sound has stopped. Let's take, for instance, the thunder. The moment you hear the sound from thunder, it would have occurred like 10 minutes ago, but you still hear the sound repeating itself continuously. And the more it repeats itself, you see the sound keeps on repeating itself, and gradually the volume or the intensity of the sound reduces gradually. We call it multiple reflection of sound. That is, it is almost similar to echo, but this one, the intensity reduces continuously, gradually, but the reflection is there. That is, you hear dum, 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 dum. So that means thunder is a typical example of revibration. We'll go to the next one. On the next slide, we're going to now talk about ultrasound, or what we simply call ultrasonic wave or infrasound. We're going to talk about ultrasound. We're going to talk about infrasound. For ultrasound is a wave or sound wave that has a very high frequency. When we're talking about a very high frequency, we're talking about a frequency of about above 220,000 Hz. This is beyond the human hearing ability. That is, for us human, we cannot hear this kind of sound. And that is why you discover that there are times you discover that in the night or in the daytime, the cats tends to reciprocate back when they hear that sound. And you think whether it is a witch. No, it is not a witch. It means that the cats, the dogs, have heard sound that you cannot hear. So ultrasound are sounds that are created whereby the frequencies are very high, that is above 20,000 Hz. This ultrasound because the frequency is high, you should know that the wavelength should be short. So therefore, we can say that the applications of ultrasound can also be beneficial to us. One application is that we can use it in the industries, we can use it in medicine, that is in the hospital. In the industry, we can use it to kill bacteria during what we call purification. We can also use it in the industry to locate cracks or defects in metals. In the hospital, which is in medicine, we can use it during pregnancy. If you see a pregnant woman, maybe after the first trimester or the second, they will tell her to go and do an ultrasonic test or scan. When she goes there, she is being made to lie on the bed and a liquid jelly is being placed. A cold liquid jelly is placed on her tummy and the device is being moved around her body. What it does is that it sends sound to the tummy, and where there is a fetus, that is where the baby, unborn baby is moving, it will show the baby on the monitor of the ultrasound. And with that, you can now tell if the baby's, you can even determine the baby's sexes, whether it's a male or a female. You can determine if the baby is healthy or not. You can determine the position of the baby even before delivery. You can also even determine the relative average age of the baby. That's why they will tell you whereby a woman is pregnant 4 weeks, 8 weeks, 10 weeks, 24 weeks, and so on. Now, ultrasound is very important. Why? Because it can even tell you, like the men, we can go to the hospital and they will ask us to go and do ultrasound. Why? Because maybe there is something the doctors are not saying within our tummy or our stomach, or our body parts. They can use ultrasound to check if there is anything wrong with any of the tissues, the soft tissues in us. So we'll now go to the next one, which is infrasound. For infrasound or infrasonic is talking about a very low, is the opposite of ultrasound. If ultra is a very high frequency of above 20,000, infrasound is a very low frequency of below 20 Hz. Still, the sound of this frequency cannot be heard by humans. But there are animals like whale, elephants that can sense or hear these sounds, and they even use it for communication. If you have watched some movies, you will discover that even animals like whale tend to communicate, and even us don't hear them. Why? Because the sound they use to communicate is infrasonic. It is less than 20 Hz. This sound can also be used for what we call to detect volcanic eruption. That is, whereby there is a crack due to the volcanoes deep down the soil. It can be detected using infrasonic wave. With this, we can now say that the difference between ultrasound and infrasound is that ultrasound is of high frequency of 20 Hz, infrasound is less than 20 Hz. With this, I would like to come to the end of this class, and I will beg you to please read your notes, read more, practice more exercises, and therefore I wish you best of luck in your exams. Thank you very much.